Welcome back, my degenerate eigenfollowers. So today I'm going to be doing something a little bit different. I've released a few videos on quantum mechanics in the past here, but I've decided that I want to take this to another level and just designate an entire series. So to do that, I want to sort of back up a little bit and start going over some of the concepts that maybe I didn't emphasize enough. So today we're going to start out with normalization, and then we're going to do a problem after that. So let's get to it. Alright, so as I've discussed very briefly before, normalization is a condition that ensures the particle exists within some region of space. You have what's called a probability density, and you use that as a way of summing up all possible points in space to determine where the particle most likely resides in. So if we were to write that out quantitatively, we're going to have that was a huge integral. We're going to have some integral from negative infinity to positive infinity, where we have the square modulus, or the probability density. That's a function of x and t with respect to x. And if we want to, say, just extend that out a bit, we can decompose that square modulus term as psi star, which is the conjugated part of the wave function, because we're dealing with complex numbers, and psi with respect to x. Okay, so this, if we are to preserve the statistical interpretation of quantum mechanics, well, we necessarily need to invoke what's called Bourne's statistical interpretation, and this sort of demands that this be equal to 1. And for that to be the case, the particle must exist somewhere, therefore the statistical interpretation is preserved, and we have a physically realizable state, and that is a very central sort of facet of quantum mechanics that is going to be popping up very frequently, as you may have already noticed. So what does that look like pictorially? Well, we can take some wave function, and rather, if we were to have normalized this wave function, and let's say we have some parabola that is just extending out to infinity without bound. Well, if it's forever diverging and extending out to infinity, well, then we have a non-normalizable state. So essentially, as x approaches infinity, then we have basically a non-normalizable state. And this is something that comes up. It's not unheard of. In fact, it is something you see when talking about scattering states or free particles. And these are examples of those kinds of situations, which we'll see later in this series. And these are basically the only sort of reconciliation of something like this is to express your wave function as a linear combination of time-dependent states, basically. But once again, we'll get to that later. So we have another condition that the wave function must preserve, and that is as x approaches infinity, our wave function approaches 0. Okay? So this, once again, it sort of preserves the physical sort of reality that we live in. So essentially, infinity is not necessarily something that you can reconcile unless the wave function just vanishes at that point. So now, there's a natural question that arises when you're talking about the normalization condition, and it's that, how does the Schrodinger equation know that the wave function stays normalized just for an arbitrary amount of time? So given some evolution of time, how does the Schrodinger equation guarantee that the wave function remains normalized? Well, that's what we're going to prove here. So let's take our normalization condition. So we have negative infinity to positive infinity, where we have psi squared here with respect to x. And what we're going to do here is we're going to differentiate this term here with respect to time and see what happens, right? We're going to see how time affects these normalization conditions here. So we're going to have dt, and we're going to bring this under the integral sign. And if you recall from the video I did on the Leibniz rule for integration, you know that we can bring this under the integral sign. So we're going to have our integral from minus infinity to positive infinity, and because psi is a function of x and t, we're going to turn this into a partial derivative. And we're going to have psi conjugate times psi with respect to x. Okay, so what can we do here? Well, let's just do product rule, right? And I'm just going to focus on the integrand here, and then I'll put the integral back later. So what we're going to have now is we're going to have d partial d psi dt and psi plus we're going to have psi star d psi dt. Okay, so this, we're going to have to figure out what to do with this here. So this is when the Schrodinger equation comes into play. So we have, let's bring out the time-dependent Schrodinger equation, which is I h bar d psi dt, and that is equal to negative h bar squared over 2m. I'm going to run out of room here. Over 2m, and then that's d squared psi dx squared plus some potential and multiplied by our wave function. Okay, so we see we have these time-dependent differentials here. Let's solve for d psi dt. Okay, so let's bring this all over. We're going to have d psi dt. Alright, well, if we divide out that imaginary part here, I'm going to bring it up to the numerator, which cancels that negative sign. So we're going to have h bar over 2m times d squared psi dx squared, and that is going to be minus I over h bar v psi. Okay, so we have our first equation that we're going to be popping in there. Now let's basically take the conjugate, because we have our, basically we have this d psi dt term. So let's just conjugate this. So we're going to have 2 for that one. So d psi star dt is equal to, oh, I just realized there should be an I here. I'm sure you were all screaming at me. So this is going to be equal to minus I h bar over 2m d squared psi, and that's psi star, dx squared plus I over h bar, and that's v psi star. Alright, cool. So now we have our conditions. Let's start plugging them in here. So this is going to go there, and this is going to go there. So we're going to start out with our conjugate term. Let's bring this down here. So first one, we're going to have negative I h bar over 2m d squared psi star dx squared plus I over h bar times our potential v psi star, and we're going to close that off here. And on the outside here, if you see, we have a psi term here, so psi, and we are going to be adding that. So plus we're going to have psi star now. So we're going to put in the non-conjugated term. We're going to have I h bar over 2m d squared psi dx squared. That's not a plus, that should be a minus. Oops. Alright, so minus I over h bar v psi. Alrighty, so right away we can see that there's going to be some cancellations. After we distribute these psi terms in here, we can cancel our potential terms, basically. And now I want to put this all together back under the integral sign. So I'm going to factor out the common factor of I h bar over 2m, since they're constants, and we're going to pull that out of the integral. So we're going to get I h bar over 2m with some integral from negative infinity to positive infinity, where now I'm going to rearrange this. We're going to have d squared. Actually, let me try to do this first. So we're going to have psi star, where we have d squared psi dx squared, and that is going to be minus d squared psi star with respect to x squared times psi. Alright, and that's all with respect to x. So, almost done here. Now what we're going to do is we're going to factor out the common ddx terms. And normally, it's not necessarily factoring, but what you'll see, this statement is in fact correct. Because if you were to say, let's see, we're going to pull out this ddx term, right? And that's going to give us psi star d psi dx minus d psi star dx psi. And if you were to apply this differential back in here, you'd basically have to take product rule to both of these terms here and both of these terms, and what you'll see is there's a common factor that cancels out, and it just leaves you back with this. So this is in fact true. So we can do that. So we're going to integrate that from minus infinity to positive infinity I h bar over 2m dx. Alright, so now at this point, the differential term on the outside, ddx, undoes the integral sign. So what we're left with is I h bar over 2m, where we have our limits, and all we're left with is psi star d psi dx minus d psi star dx psi. Alright, and what we can see here is if we were to apply these limits, well, this basically brings up our enforced condition for a physically realizable state for the wave function. So in what you'll see here is as x tends toward infinity, psi must tend towards 0. And what we end up with is all of this tending towards infinity when we substitute our limits in, and that just gives us 0. So in other words, d dt, so of our limits from negative infinity to positive infinity of psi squared dx equals 0. And there you have it. This shows us very clearly that the wave function does not depend on time. So because we have a constant here that is 0, so that very clearly validates the normalization condition, suggesting that the wave function or the normalization does not change for an arbitrary amount of time. So there you go. That validates the normalization condition. And next here, we're going to work through a brief example, and we're going to kind of get an idea how this works in practice. Alright, so we have our problem. Well, what we have first is our wave function, set up in sort of like a piecewise sort of function. And our boundaries from a to 0 where basically x is equal to a, well, between a and 0, our value is going to be a times x over a, and then our bound where x is between b and a is going to yield a times b minus x over b minus a, and anything outside of those bounds is going to be 0. And now what we want to do is, with that, we're going to normalize our wave function and find what a is. And we're going to sketch that wave function, and then determine the particle's most likely location at t equals 0. And then, similarly, the probability of finding the particle to the left of a. And then check the limiting cases where b is equal to a, and then b is equal to 2a. All right? So let's sort of partition this off here and start going. So we know that our wave function condition from negative infinity to positive infinity of our square modulus term here with respect to x is equal to 1, right? Well, as you can see here, our boundary conditions are a little bit different than what we have here. So anything below 0 is going to yield 0. So we can eliminate anything beyond that point. And similarly, anything outside of where b is also going to be 0. I suppose b could be infinity, but we're keeping it pretty general. So let's start setting up our conditions. So we're going to have some integral from 0 to a, where we have a squared, and then times x squared over a squared with respect to x. And we're going to add that to this term right here. So changing our bounds from a to b, where we have, yet again, a squared times b minus x squared over b minus a squared with respect to x. And at this point, we can just solve these integrals explicitly. So let's take this term out, and I'm going to remove some of these non-x dependent terms. So we're going to have our a squared, and that's going to be the integral from 0 to a, where we have x squared over a squared dx plus, oops, I forgot to pull those constants out. Try that again. We're going to have a squared over b minus a squared with our integral from a to b, where we have b minus x squared dx. Alright, so now what we want to do is just integrate these, right? So our first term, we're going to have a squared, take the antiderivative from 0 to a, gives us x cubed over 3a squared dx. And on the outside here, we have a squared over b minus a squared. Alright, so before we take this interval, I suggest we just do a little bit of u substitution, where we have u equals b minus x, and du is equal to negative x dx. And not negative x, sorry. It's negative 1. Negative 1. Sorry about that. Yeah, so negative 1, so just negative dx then. And if we plug those in, we're going to have from a to b, we have negative u squared du. I'm not going to change the limits just because I'm going to substitute this back in. So we can already solve for the first term here, and when we plug in our limits, this a squared term is going to cancel, and what we'll be left with is just a times capital A squared over 3. But now we have this term here. So this just becomes from a to b, where we have u cubed, but u is just b minus x, so we're going to have minus b minus x cubed over 3. And if we substitute our bounds in, we're going to get, I'm going to pull out the 1/3, substitute those bounds, we're going to get negative b minus b cubed minus b minus a. Running out of room on an infinite whiteboard. B minus a cubed, and yeah. And what we see here is that this just becomes 0. You add those up, and you just get b minus a cubed. Cool. Now, when we plug this all back in over here, these terms are going to cancel with that, and we are going to end up with a squared times b minus a over 3. Cool. Alright, now we can also keep in mind that this is equal to 1, right? Now let's factor out a common term of a squared over 3, and that is going to give us just a plus b minus a, where a's cancel here, and we'll call this is also 1. So what we end up getting for our normalization constant, a is going to be equal to 3 over b to the 1/2. So the square root of 3 over b. So there we go. That is the value for our normalization constant. Now, let's substitute this into our conditions for the wave function here, right? Because now what we want to do basically is sketch the wave function at t equals 0, right? So what we're going to have here for our first term from 0 to a is going to be 3 over b, and we're going to have just x over a. Yeah. And oops. And this is going to be from a to 0. And our first term is this, and then our second term is going to be 3 over b. And I believe that was b minus x. B minus x over b minus a. So b minus x over b minus a. And this is from a to b. And we can now sketch this out. Alright, so what does this look like? Change the width of my lines here. So we're going to have some wave function, and our domain is going to be x. So some wave function as a function of x, where we have a and b somewhere along this line. So we're going to have a and b. And what we'll see here is that the wave function gradually increases up until the point that it hits A. Okay? And once it hits A, it steeply declines all the way to B. And that's basically what it looks like. And what we want to figure out now is just determine the particle's most likely location at t equals 0, and then the probability of finding it to the left of A in our limiting cases. Alright, and what we'll see here is now from A to B, well, the most likely location of that particle is simply just going to be right at A. And you can see this pretty clearly if you just substitute A in for X, right? And basically those all cancel, and what we're left with is just a normalization constant. Where it peaks, where basically both lines intersect, that's going to correspond to the most likely location of our particle, right? So now what we want to know is what is the probability of that particle existing to the left of A, right? Well, using our limiting cases, where essentially B is equal to A, we can see what that's supposed to look like by just imposing our normalization condition yet again. So if we have, say here, if B is equal to A, then there's no B term. This pretty much goes away, and we're just left with this triangular term, or triangular sort of section of our wave function. And this is going to be from 0 to A, and we're going to have 3 over B, but B is A here, so 3 over A times x squared over A squared with respect to x. And what we can see here now, after basically solving it, we're going to have 3 over A cubed from 0 to A. We're going to have x cubed over 3. Well, if we plug in our limits, that just gives us A cubed over 3. These 3's cancel, and so do these. So that would just be equal to 1. And that makes sense. If you look at the graph we have here, if we're only concerned with to the left of A, where B is equal to A, there's a 100% chance that the particle is going to be within that region of space to the left of A. So it basically guarantees that condition. Similarly, if we have B is equal to 2A, well, you can sort of see from the integral we've just done, right? So if B is equal to 2A, everything's going from 0 to A, right? Well, if we have A in here, we can basically plug in 2A for B, and we have 2A cubed, and basically what that ends up giving us when we make our cancellations is 1/2. And that makes sense, because we can essentially realize when we have that condition, our graph is now going to be symmetric. There's not going to be a steep decline. So we're going to have A and 2A, where at this point, that's not very symmetric. I'm sorry, I'm really bad at graphs. Yeah, so basically we have 2A here. And that makes sense, because where is that particle going to reside between those points? Well, it's going to be somewhere halfway in between. So it gives you a 50% chance of locating it there. So I brought up Desmos here so you can sort of see a little bit more cleanly what this is supposed to look like, where we basically have A is equal to 2 and B is equal to 4, just some arbitrary selections here for our A and B values. And what we see here is that A, rises here and then sharply declines when it basically reaches those interval points. And right where it intersects in this case, if A is equal to 2, right, Well, you can see that this corresponds to the most likely location where the particle must exist. But if we have 2a, well, then we yet again have a symmetric outcome here. So in essence, we can sort of shift this and they're going to remain symmetric about their center, which corresponds to a 50% likelihood of determining that particle, of locating that particle at those at the intersection here. So that's just what I wanted to at least sort of get across here, just if it wasn't entirely clear from my drawing here. Alright, well that just about does it for this video. I hope you gained something of value here and maybe learned something today about normalization, and in the next video we're going to be going over operators and expectation values, some other very key facets to quantum mechanics, and then we'll, as before, we're just going to work out some more problems, and then as we proceed, we are going to be looking at some important problems in quantum mechanics, like the quantum harmonic oscillator, and just talk about the Heisenberg uncertainty principle, things like the Dirac delta function, all of that good stuff there. So stay tuned, and see you later, calculator.